Yeah, hello everyone. In this lecture, we will study the binomial coefficients. So, by definition, the binomial coefficients just a combinatorial number, or n choose k. More explicitly, first we recall some basic properties of n choose k. The first one is kind of symmetric property. You can also see this from the Pascal triangle. And the second one is total summation is 2n. Or if you write down the Pascal triangle, the summation of the numbers in the same line gives you the powers of 2. So first one means that symmetric along the y-axis. Symmetric. You reflect along the y-axis or the center line, you get the same picture. The second one means the summation. So here is 2 square. Summation is always the power of 2. And then the third one is the induction relation or iterated relation. That is, n choose k equals n minus 1 choose k plus n minus 1 choose k minus 1. So in the picture, it means that each number equals the summation of 2 numbers on its shoulders. Okay. We already proved these properties before, so I will not repeat. Okay, next, let's look at easy application of the combinatorial numbers to do with some real problems. So first, we already know how to compute the summation from 1 to n. This is n times n plus 1 divided by 2, which is n plus 1, or choose 2. This is actually known. I don't know if it's known to people earlier, but it said Gauss derived this formula when he was 7 years old. Okay, next one is not that transparent, but we can derive this based on the previous formula. So first, noted that when you do n plus 1 square minus n plus 1 cube minus n cube, you do distribution, you do have 3n squared plus 3n plus 1. If you have n cube minus n minus 1 cube, you have 3n minus 1 squared plus 3n minus 1 plus 1. Keep on going, you have k cube minus k minus 1 cube equals 3k minus 1 squared plus 3k minus 1 plus 1. equals 3 times 0 plus 3 times 0 plus 1. And now if you sum them up, so on the left hand side, you have here you have cancellations. Therefore, finally, you have n plus 1 cube. On the right hand side, you have 3n squared plus n minus 1 squared plus all the way to n squared plus 0 squared and plus 3n plus n minus 1 plus all the way to 1 plus 0. And you have many 1s. So how many you have? Let's count how many items, how many equalities you have. So this is first equality, second one, case 1. Sorry, this is not case 1. So this will be n plus 1 minus k. So n plus 2 minus k. Yes. Okay, therefore this is n plus 1. N plus 1. Okay, and therefore here you plus n plus 1. Okay, if you look at left hand side and right hand side more carefully, you will see we do have formula for this summation, and this one is exactly what we want to know. Therefore, if you move terms, collect terms, you will have n squared plus n minus 1 squared plus all the way to 1 squared equals n plus 1 cube minus 3 times, let's use Gauss formula. So here you have n times n plus 1 divided by 2 minus n plus 1 divided by 3. And then if you simplify it, you have n plus 1 times n, n plus 1, 2n plus 1 divided by 3. Okay, sorry, divided by 6. Okay, so let's make several remarks. First remark is, it's easy to see by induction, you can compute the summation for a fixed integer k greater than or equal to 1. This will be a formula dependent on k and n. Okay, by induction you can derive the formula, but probably it's not that easy. I suggest you to try out when k is 3 and to get familiar with this method. Secondly, I thought this formula was known to ancient Greek people many thousand years ago, because at that time they already know how to calculate something like equivalent to the integral. For example, they know how to calculate integration from 0 to 1 x squared dx. In other words, they know how to calculate the area of the shaded region underneath parabola. So how did they do that? the only thing they can do is just like what we learned in calculus. We cut the region into small pieces and approximate, use small triangles, small rectangles, and you have n, and let n goes to infinity. You cut final and final. You expect the summation of the area of rectangles give you approximate area for the blue shaded region. And if you do sum them up, you do have something equivalent to this. Okay, and finally, by the formula here, so I will say, let's do it once. For example, suppose we cut the blue region into n pieces and approximate by green rectangles. And then the summation, the Riemann sum of the small rectangles give you k square, k over n square divide times 1 over n, k from 1 to n. So this is a Riemann sum. Okay, and by the above formula, apply this formula, we can actually compute it. This will be 1 over n cubed times n plus 1, n times n plus 1 to n plus 1 divided by 6. Okay, now if n goes to infinity, in other words, you cut the region into smaller and smaller pieces. And now, what is the answer? It's easy to see the answer is 1 over 3. On the other hand, nowadays we can use Newton's formula. So this is Newton-Leibniz formula, x cubed divided by 3, and evaluate at 2 endpoints. That will be 1/3. Okay, but with the consideration that in the ancient Greek time, there's no calculus at all. So it's a fantastic advantage. It's a fantastic that people know how to calculate the area for the blue region. Okay, now we turn to the main topic for this lecture. That is binomial theorem. So why we call it binomial coefficient? This is because you can see from this theorem, those appears as the coefficients when you expand power for some linear function with 2 terms. Okay, for x, y real numbers and integer n greater than or equal to 0, when you expand x plus y to n's power, of course, each monomial will be a polynomial of degree n. And then the only thing we don't know is coefficient, But now the theorem tells you the coefficient is exactly the combinatorial number plus n choose 2 xn minus 1 times y squared plus all the way to n choose n minus 1 y n minus 1. Let's write n choose n y to n's power. And if you want a more concise form, there will be summation for k from 0 to n choose k x to n minus k times y to k's power. Okay, and the first proof, in your exercise, sometimes they ask for a combinatorial proof. What does combinatorial proof mean? That means you construct a model combinatorial problem, and then from solving that problem, you derive the answer, just like the following. So you write xy to n's power like x plus y times x plus y times all the way to x times y. So totally you have n x plus y's. And to compute the coefficients for the item x n minus k times y to k's power, so you will see the coefficients is equivalent to the number of ways we derive this monomial. So how many ways to derive this monomial when we apply distribution law. So here k is integer numbers from 0 to n. And you will see this is equivalent to see that how many ways to pick ky's from the product. So let's call this product star. Okay, then it's easy. It's just n choose k. Okay, so the combinatorial proof usually not that rigorous because different people might have different understanding. You might have a hard time to explain why these two problems are equivalent. But for yourself, this is a very efficient way because at least for new problems, you can guess the correct formula. Okay, as soon as you have the correct formula, you can manually cook up some more rigorous proof. So for example, as soon as we know the formula, we can prove it by induction. When n is 1, this is trivially true. And suppose it is true when n equals m. That is x plus y to m's power equals summation k for k from 0 to m, m choose k times x, m minus k, y to k's power. And then when n is m plus 1, we consider the power function x plus y to m plus 1's power. You rewrite it as x plus y times x plus y to m's power. Then you can apply the formula or substitute formula. When n is m, x minus k times y to k's power. Then do distribution law. You have so you should do x times this and y times this. So first you have summation for k from 0 to m choose k, x m plus 1 minus k times y to k's power, plus summation for k from 0 to m choose k, x m to m minus k times y to k plus 1. Okay, next, let's change the coefficient. So let's keep the first one. Let's change the variable k to k prime. The reason is that later on, for the formula, you only have a clear summation of monomials. Each are different, and here x to m plus 1 minus k times y to k's power may equal, this equals x m minus k minus 1 times y k minus 1 plus 1. So if you let k to be k minus 1 in your second term, they are same. So you need to combine the coefficients. Okay, how to combine it? So here we introduce a new variable like k prime, or shift k by 1 in some regular language. So let's see. Let k prime be k plus 1. Yeah, be k plus 1. Then here the bound will be k prime starting from 1 end up with m plus 1. And here you have k prime minus 1, x to m plus 1 minus k prime, and y to k prime. Okay, and the items now are similar, but the only possible problem is the range for k is different. Here for k is from 0 to m, for k prime is from 1 to m plus 1. And then next we extend the region to 0 to be from 0 to m plus 1. So what we will have? Fortunately, we have the same formula. The reason is that, I will first explain to this. When k is m plus 1, m choose m plus 1 times xm to m plus 1 minus m plus 1 times ym plus 1 is 0, because this is 0. Okay, so it doesn't affect your function when you extend the region for k from m to m plus 1. And similarly, for k prime, you can extend from 1 to 0. Okay, and for simplicity, we rewrite k prime as k. Okay, if you first time met this technique, probably you will get confused why we have k and k prime, then you get k back. Okay, but actually what we were doing is shift the parameter by 1. Okay, same reason. When k prime equals 0, m k prime minus 1 is m choose minus 1, which is 0. Therefore, it doesn't matter when you enlarge the region. Okay, now you can combine the coefficient m choose k plus m choose k minus 1 x to m plus k minus 1 times y to k's power. And here you use Pascal identity. So that gives you summation for k from 0 to m plus 1, m plus 1 choose k, x m plus 1 minus k times y to k's power. This is exactly the formula we want for induction. Okay, just a remark. Please deduce this by yourself to get familiar with a shifting technique. So this is a shifting technique. Let's use a different color. The shifting technique. Shifting. Okay. Okay, next remark is about the formula itself. When you let y equal 1, then what we have is 1 plus x to nth power equals 1 plus summation k from 1 to n, and choose k times x to k's power. And if you learn Taylor expansion before, then you have more general formula even for, so here n is greater than or equal to 1, for instance. And we can also do this for negative integers. So this is negative 1 to k's power, k from 0 to infinity, m plus k minus 1 to k's power times x to k's power. Okay, and if you choose x to negative x, then you have a cleaner formula. N plus 1 minus 1 choose k times x to k's power. Notice that here you have infinite sum instead of a finite sum. Okay, and when the norm of x is small. Actually, smaller than 1 is enough. We can extend this formula even to non-integer index, non-integer power. N is not an integer. For example, 0.5. Then we will have the Taylor expansion. The formula is same, and the problem is how to derive the coefficient. So the coefficient by Taylor expansion, there will be the case derivative, and after you take the derivative, you substitute in x equals 0, and that will be your coefficient, and then times x to k's power. K is from 0 to infinity. And if you really compute it, you will find this is exactly the number. N times n minus 1 all the way to n minus k plus 1 divided by k factorial when k greater than or equal to 1. And it's 1 when k is 0. It's 0 when k is less than or equal to negative 1. And notice that here n is not necessary to be an integer. And later on, if you let's make another remark to a remark. Later on, if you learn the gamma function, different from gamma function, similar. Let me use a different color. But different from the gamma function. You can search online what is gamma function. Okay, and if you look back all the properties we have, you will see actually the Pascal's formula can be extended to real number n divided by k equals n minus 1 choose k, n choose k equals n minus 1 choose k plus n minus 1 choose k minus 1. And the question left to you is that, so which properties extend to real number n as well? You can check all the properties we had and to see if that holds for real numbers. Next, let's do some tricky application. Actually, when you do some theoretical proof for some combinatorial formulas later, sometimes they use very tricky transformation between binomial coefficients. So it's good to give you some flavor of what that work in this lecture. Yeah, and also some people want us to give some model solutions for the homework, which I prefer not, because that will restrict your mind. Like most of the problem will have alternative answer. So even if you get back your result, get back your homework grading, I expect you to think about more and discuss with people, not just look at the solution paper and remember it. That's not a good habit, because now you are not in 235 two-level classes. It's a more advanced course. The purpose is give you some training. Even you, after all the material we learn in this class, you are still left something to deal with the problems in your later studies, no matter you are in you major in math, science, computer science, statistics, or whatever, chemistry or whatever. And choose M. The answer is n times 2 to n minus 1's power. Okay, so first proof. The annoying thing is, notice that the annoying thing is here you have different coefficients before the binomial coefficients. If you don't have that, you just have the power of 2. Okay, and then if you don't like it, think about how to remove this. So here's one of the methods. Noted that k times n divided by k is k times n. Sorry, k times n choose k is k times n choose n minus k, which is k times n minus 1 all the way to k plus 1 n minus k factorial. And if you rewrite it, you can have n times n minus 1 times all the way to k plus 1 times k divided by n minus k factorial. That would be n times n minus 1 choose n minus k, or n times n minus 1 choose k minus 1. Therefore, if you plug in, you will find, let me denote this as L. So now L equals n times n minus 1 choose 0 plus n minus 1 choose 1 plus n minus 1 choose n minus 1. So that gives you 2 times 2 to n minus 1's power. Okay, and second proof. This is another general idea, which is called generating functions. You incorporate your numbers into a function as the coefficients for the monomials, and then when you do some summation or whatever, you just realize it as evaluation or some derivation of the functions. So, for example, here, let's consider a function 1 plus x to n's power. Okay, and if you write it in this way, you can view this as an infinite sum. Although, in fact, we have more explicit expression for AK. AK is n choose k. Therefore, when k is greater than or equal to n plus 1, AK is 0. Okay, and now, what we want to know, we can write as L is n choose 1 plus 2 times n choose 2 plus all the way to n times n choose n. This is summation k from 1 to infinity, k times AK. And what is this? notice that this is exactly the derivative of the original function k times a k times x, and set x equal 1. Okay, in other words, we can rewrite the L equals 1 plus x to nth power, take derivative, and evaluate at point x equals 1. Okay, then if you really do the computation, that gives you n times 1 plus x n minus 1, evaluate at x equals 1, and when you plug in, you have n times 2n minus 1 factor, 2 to n minus 1's power. Proposition 2. Similarly, we can consider the summation n choose 1 plus 2 square n choose 2 plus all the way to n square n choose n. Let's still call it L. And what is the number for L? I will give you the proof for the similar to the first proof of proposition 1. So first, we rewrite L into the following form. So 1 times 0 and choose 1 plus 2 times 1 and choose 2. The reason we do this is because we would like to apply the similar argument twice. And here, what we have is n choose 1 plus 2 times n choose 2 plus n times n choose n. The answer for the second line, the value for the summation in the second line is just a proposition 1, and all we need to do is evaluate the summation of items in the first line. So let's call this S, and recall that k times k minus 1 and choose k is k times k minus 1 and choose n minus k. So if you, let me write it in this way, k minus 1 times k. And then here you have k minus 1 times n minus 1 k minus 1. Okay, then you have, this is n minus 1 times n minus 2, choose k minus 2. Therefore, S is n times m, sorry, here you have extra n. N times n minus 1 times n minus 2, 0, plus n minus 2, choose 1, plus n minus 2, choose n minus 2. This is n times n minus 1 times 2n minus 2. Okay, and then the summation L is n times n minus 1 times 2 to n minus 2 plus n times 2 to n minus 1. Okay, and if you want to simplify it, it's n times n plus 1 times 2 to n minus 2. Okay, and the second method, I leave it to you, and which is by interpret the formula as the coefficients for some functions, and you consider 1 plus x to nth power and consider 1 plus x to nth power, the second derivative of this function, and blah blah. You should expect the same result. Okay, next interesting property that we can sum up the sum of squares of n choose 0, n choose 1, all the way to n choose n. This is 2n choose n. And here, if you look, the combinatorial proof will be easier. Of course, by induction, I guess you can also derive a more rigorous mathematical proof. So, on the right-hand side, it's just a simple 2n choose n problem. And from the left-hand side, we just cut the 2n positions, 2n objects, divided 2n objects into two parts. So first n objects, second n objects, and then you may have the following. Following properties, that is, you choose 0 objects in the first half, and then you choose n objects in the second half, or you choose 1 object in the first half, n minus 1 object in the second half, and lastly you choose n objects from the first half, and then 0 objects in the second half. Second half. Okay, so if you reformulate the problem, ways to choose n objects from 2n objects. So this is a set, is a disjoint union, or have a partition as following. For k from 0 to n, choose k objects from the first n objects and m minus k objects from the second n objects. Okay, then you just interpret the formula we want to prove as a combinatorial problems. And left-hand side, it's easy to see, it's 2n choose n. And the right-hand side, because it's partition, so you can use, by the addition formula, addition principle for enumeration, you have summation for k from 0 to n. And then for each small problem, there will be n choose k times n choose n minus k. And you change it a little bit, you just have the formula we want to prove. Because n choose n minus k equals n choose k. Yeah, this idea is very simple, but quite useful. I also use that in my paper. Okay, next very important property you can also see from the Pascal triangle is that it's called Unimodality, Binomial Coefficients. That is, if you have the triangle, you will see that along each line, along each row, the value goes up and then goes down. And if you count how many peaks you have, when n is even, you only have one peak, 2, for example here, peak. And when n is odd, you have 2 peaks. Okay. So next, we rigorously prove this observation. Suppose n is a positive integer. If n is even, then we have the strict inequality and n choose n divided by 2 greater than n choose n divided by 2 plus 1 all the way to n choose n. The second half actually is trivial because we know it's symmetric. So for example, n choose n, just n choose 0. Okay, the non-trivial part is the first half. And similarly, if n is odd, we have n choose 0 less than n choose 1 less than all the way to n choose n plus 1 divided by 2. Oh, sorry. Here's n minus 1 divided by 2 equals n choose n plus 1 divided by 2. Okay, then n choose n plus 1 divided by 2 greater than n choose n plus 1 divided by 2 plus 1 greater than all the way to n choose n. Noted that by symmetry, these two numbers must be the same. Okay, so that's why we have 2 peaks when n is odd. Okay, so the proof is easy. Just like when you want to compare 2 numbers, you have 2 common ways. First, you do subtraction. If the subtraction is positive, then the first one is greater than the second one. This is the first method. And second method, you take the quotient. If the quotient is greater than 1, then the numerator is greater than the denominator. So here, because from the definition, the combinatorial numbers, binomial coefficients, are product divided by some other product. So probably it's easier to compare the quotient. So we consider the quotient of adjacent binomial coefficients. And so let's call it Q, for instance. So Q equals n times n minus 1 all the way to n minus k plus 1 divided by k factorial. And then you divide by n times n minus 1 all the way to n minus k plus 2 divided by k minus 1 factorial. Therefore, if you cancel out factors, you have n minus k plus 1 divided by k. Okay, then if n minus k plus 1 less than or equal to k, then n choose k minus 1 is greater than or equal to n choose k. And in particular, if the inequality is strict Then you also have a strict inequality between binomial coefficients. And similarly, if the coefficient, if n minus k plus 1 is greater than or equal to k, then you have the reverse inequality. And also, if the inequality is strict, then the inequality between binomial coefficients is also strict. And now, if n is even, then you will see n minus k plus 1 greater than k for k from 0 all the way to n divided by 2, and less than k for k from n divided by 2 plus 1 all the way to n. Okay, therefore you have a single peak at n over 2. If n is odd, n minus k plus 1 greater than k for k from 0 to n minus 1 divided by 2, and n minus k plus k equals k for k equals n plus 1 divided by 2, and less than k for k equals n plus 1 divided by 2 plus 1 all the way to n. So that gives you two peaks in the middle. Okay, we are done. To conclude this lecture, we just will introduce a useful notation, which is commonly used in computer science and mathematics, which is called floor and ceiling. So suppose x is a real number. We define floor as the greatest integer that is less than or equal to x, and the ceiling is the smallest integer that is greater than or equal to x. So for example, for n divided by 2, if you take the floor, it's n over 2 when n is even. It's n minus 1 over 2 when n is odd. And the ceiling is n over 2 when n is even, n plus 1 over 2 when n is odd. And also, for example, for minus 3.1, the floor is negative 4. Positive 3.1, the floor is 3. Negative, the ceiling of negative 3.1 is negative 3. The ceiling of 3.1 is 4. Okay, in this notation, we have the following, which is part of the result in the previous theorem. That is, n choose n over 2 floor equals n choose n over 2 ceiling, which is the largest among all binomial coefficients. Okay, I will stop here for this lecture.